So when bank lends you money and lends to other 300 or 4,000 people money, yeah, they compound that exponential growth. So you heard it before. If you have money, you make money. It's a very simple statement. Why? Because of exponential growth. It's very simple, right? We can take a look at that. We can look at the problem now involving money. Say, how long does it take to double the investment at 4% in a year? And we are going to use continuous compounding, so we're going to use the E equation, right? How long does it take you to double the investment? Okay, well, we have our exponential growth. It is A equal PE. We usually use RT, and R is the rate, which is the same as K. We just use R now. In our case, it's going to be 0.04 because that's what the 4% is. Don't put 0.4, that's 40%. 0.0, it's doubled. So now the P cancels. That's why I never asked you to invest $1,000, right? I just said to double your investment. And because I don't know how much money you have to invest. Maybe you have $100, maybe you have $1,000, maybe you have $10,000, right? And now you have 2 equals, leave space, E 0.04t, hit both sides with ln, and now we can calculate the ln of 2 and then divide it by 0.04. So ln of 2 is going to give me 0.6931 equal to 0.04t. Divide that number by 0.04 and get t equals 17 years. So you have to wait 17 years to double the money, right? And you go, well, that's a long time. And you go, it's money. How long since it's been since Bill Gates retired? How much money did he have when he retired? It was about $50 billion. What does he have today? About $83 billion. What does he do?
Nothing.
He runs.
He makes lasers to kill mosquitoes.
He runs foundation, right? He runs foundation that gives away money.
What?
Bill and Melinda Gates Foundation, right, gives to Rotary $250 million every year, writes us a check of $250 million every year. He runs, he gives check to Khan to run Khan Academy. He gives like a whole bunch of money, right? See, when you have a lot of money, it immediately generates more money, right, with investments. So he has been retired for a decade, right? And in his retirement, while giving away the money, because he said kids are not getting anything, obviously, it's his money. He is going to, he made $30 billion in retirement while giving away billions every year, right? If he writes a check to Rotary International on $250 every year, and he's doing that for the last 5 years that I know of, well, that's 1.25 right there, right? And where are the all other things that he, right? I know the first check he wrote to Khan was $1 million. So, so there's a lot of this stuff, right? You need to know. So, if Gates is to put $10 billion and wait 17 years, is going to collect 20 billion in 17 years. And you put $2, you collect 4, right? So that's the way it works. Yes?
Can we do an example with like stock market? So like for example, like mutual funds, they like boast that they can do like 10 or 12. Let's say you do better, let's say 14% compounding interest.
Yeah, you can put anything because that's just gonna change the 4 into 14. There's no difference.
What would it be?
Put 80% over here.
What would it be?
Yeah, just punch the numbers. It's the same problem. That's right. There's no difference. You come up with 14%. You come up with
5 years.
5 years. Right.
That was fast.
Well, because all you do is the 0.4 will change to 14, and it propagates through the same calculation. Still, you decide how much money you put over here, right? Now, stock market is very tricky if you have no knowledge of the world and the economy and politics especially, because you need to see the crash coming, right? If you put your $10,000 you have in a single company and it goes under, well, this is the vibe, right? Or if you put in a company that is going to, go for boom, it's great. So you put 50 cents per share, buy 10,000 shares, you see, or 100,000 shares at 50 cents, and you see that this is how, see, the difference between rich people and those who are not rich is this mentality of investment. They know that most of the investments are wasted investments, but they have money to put there, right? Again, another one of the sayings, do not put all of your eggs in one basket, right? So if there are a whole bunch of new companies, and there's always a whole bunch of new companies going public, meaning going to the market, they're going to have shares. And those shares are going to be cheap, 50 cents, 10 cents, $1, and so on. So you go and you buy 10,000 shares each. Well, we know that the failure rate of the companies is going to be 90%, right? So if you're buying 10 different companies, big chances are that 9 out of those 10 are going to go under, and that's going to be the wasted money. So let's say you have 10 companies and all of them are $1 per share, and you buy 10,000 shares each. That's $100,000 out of your pocket, knowing that you are going to lose 90,000 out of those 100,000 just because 90 or more than 90% of companies fail. But that one that makes it through, all right? If that share goes from $1 to, $20 to $26 to $40 to $100, right? That's where you make the money, right? So if you go on a market like, a noob goes on a market and buys a share for one company, well, clearly you have to fold. I mean, the mathematics of chance is there, because for every investment you make, there is 90% failure rate. Now, which one is a safe bet? Well, for the company that exists and is doing well right now, right? But their shares are extremely expensive. So you want to play the safe game for a company that is well established and is not going to fail. Well, their stocks are already $100, and then you wait 15 years, and then it's $101. So you just made pretty much nothing, right? The big gamble on the market is to find a company, to get lucky, right? And a whole bunch of investments you make, 10% of those is going to pay off, and 90% is going to fail. You just need to make sure that the one that or two that paid off, they are covering the loss from the other ones plus. So this is why who has money makes money, right? Who has money makes money, and it's very hard. A lot of dedication and hard work and wits to play that game. A lot of people. My brother used to work for a company I call the money laundering company, which is they change the one type of money into another type of money. Buy euro for dollars and then yen and yuan and rupees and all of this, right? And as you go buy and sell currencies, you make the profit. The minimum entrance to the game is 10K. You make one transaction and you lose it all, right? It's so simple, right? Then a lot of people lose that all. So let's say you are a person who worked very hard to make 10K savings, and then you just all gone in 3 days, right? Because wrong investment. You don't play with these things unless you know exactly what you're doing, right? And then you understand that there is a brokerage license that takes care of the accounts that are 100 million to 1 billion portfolio, right? And you get paid $250,000 to manage someone else's money. But you know what you're doing, so you're not messing up. So you have the pension funds and you have all of these things that you have to actually sit down and learn about these things. You can't just say, oh, I know a guy who made, $17 million playing the game of stocks, and I'm smarter than this person, right? Because you talk to this person and you're like, okay, he's an idiot, right? I can do that, I can do better. Every single thing in life has its particulars, and what they say, devil is in the details. And if you know the details, you can play the game. You can't just show up, right, and say, yeah, I got it. Here's 10K, let's go make more, right? It doesn't work that way. You have to know, you have to learn. All right, let's take a look at some other situations. So this was growth, right? This was growth. Where the money was growing. Over here, we're going to double it in 17 years. The population was growing in the previous example, right? And you can also follow the spread of a disease amongst humans, or the spread of the virus in a computer network. Like you can come up with the exponential application of growth to whatever your field is. Electrical engineering, we want to charge the capacitor, right? Charging of the capacitor happens with exponential, and then the discharge happens with the exponential model as well. And that's the capacitor going, back and forth. So now, once we are done with growth, we want to take a look at some of the decay models. Now, the first model you did in pre-calculus for the decay was carbon dating. Because you want to know how old is particular thing you dug up. If it was organic. So let's say somewhere under the rock you find scrolls, right? The scrolls are going to be made out of trees, right? And if it's organic, it's going to have the carbon isotope C14, right? Which has the half-life and 2,000 something years, whatever. And then you can calculate how old was the tree. How old was the tree that scroll was made out of? Now the tree is going to be maybe, so you can't pinpoint the hour at which the scroll was written, but at least you're going to, land within 50 years of when it's written. Because, again, you cannot guarantee that the tree, right, was the tree 3 years old, or 10 years old, or 50 years old when it was chopped down to make a scroll, right? So, the first problem you guys seen for the decay was that one. You also have seen problems for radioactive decay, and probably your problems with using the half-life. We're going to review that as well. Where you have the radioactive element of some kind, and it's just going to decay in time. So if you put everything actually decays with times, alpha radiation, right, and so on. So you have everything decays with time. You can obviously observe the banana peel decay or a few times. I had actually an apple rotting on my desk for 8 months. Actually, no, 9 months. No, 8 months. And then eventually I had to throw it away because it was started losing the form on sides. And I just wanted to see how long would it last. So I went to one of these meetings, and they had, a whole bunch of apples. I ate one, and then, I put one on the side. And I kind of forgot about it, and I was sitting in my office, and I waited. And next week or 2 weeks ago, I picked it up, and it was still like perfectly strong. I said, wow, this has been sitting on my desk here in the office for 2 weeks, and it's still perfect condition. How long can this sit here until it goes bad, right? And I posted the result on my Instagram, obviously. And I tagged it with 8-month-old with a hashtag. And it was amazing because when I click on it, it gets, there was my picture in the middle, right, of the apple, surrounded by 8-month-old babies and 8-month-old pregnant women. And my apple in the middle. It was awesome, right? Well, that's when you put the hashtag on the 8-month-old, right? And it was good, but it was decaying, it was rotting, right? So I had to throw it away after 8 months, but that's okay. So we can do those problems as well. My favorite problem of all time is problem on Doramad. Do you guys know what Doramad is? No? Oh, you're gonna love it.
I'm gonna learn today.
Yes. There it is. Doramad.
I don't see anything.
Looks like that. What do you mean you don't see anything? That's tube of Doramad. That's the advertisement for Doramad. It's the first ever tooth whitening toothpaste from 1943. Yes.
Oh, wow.
So
That's crazy.
I know, right? It was awesome. Guys, this particular toothpaste was the first effort of human race to, follow the path of beauty and smile and all of that kind of stuff. So what they did is they figured out that one of the isotopes of thorium, when applied to teeth, right, gives this wonderful white glow, and you can just smile all the time, and everyone will know how beautiful your teeth are. The problem is that thorium-229 tend to be a little bit radioactive, so everyone died, right? At which point they had to put up the new campaign to stop people from using it, because literally 100% of people that brushed died in years to come. Again, what do you know when you're in 40s? Not 40 years old, but 1940s. Watch like in 300 years, people go like, yeah, those noobs 300 years ago used to drink milk. That's why they only live 100 years. Now we, however, we're immortal. The only thing you have to do, never drop milk. Anyway, so we never know what's good, right? We have the idea of what might be good, and then we mess it up, and then we have to backtrack, right?
It's just funny. It's like evil Nazi toothpaste.
Evil Nazi toothpaste.
Killed everybody.
Yeah.
Oh my god.
Well, no, this was killing their population, right? Mainly. So, anyway, so when we go to the math and physics now, first thing we want to figure out, obviously, is the half-life of which is given in charts and tables. And then use half-life to see how fast this particular radioactive element decays. Because you just can't get rid of it, right? You can't get rid of it. So the first thing we're going to do is we're going to define the half-life, the idea of half-life and what we get from that. So we have decay problems. And as I said, you can do decay of matter, very popular video game. I just remembered a joke because, okay, so Half-Life, Valve, Gabe, right? The owner. I just remembered a joke I read that we should vote Gabe to be the president of the United States because we are guaranteed not to have World War III.
Yeah.
Right? Because there's no Half-Life 3, there's no Portal 3, there's no, right? Like all of, yeah, it's like there's nothing that the company produces. It's like 1, 2, and that's it.
That's always like compounded by the fact that it went Half-Life 1, Half-Life 2, Half-Life 2 Episode 1, Half-Life 2 Episode 2.
2, exactly. But there was no, yeah. Anyway, so let's talk about Half-Life in terms of math and physics. So half-life is the time in which right? So half-life is the time in which the initial mass is halved, meaning you have half of what you start from. So if you start with I was about to say if you start with 1 pound of plutonium, no. You put the 1 pound of plutonium together, it explodes on its own, all right? So if you start with 100 grams of plutonium, all right, and you wait the half-life, you will have 50 grams of plutonium left. So half-life is time in years. Now, there are certain particles, some subatomic particles, right, that will decay in a matter of a fraction of a second, right? So I don't want to say time in years because there are elements that decay in thousands of years. There are elements that decay within minutes. There is element that decay within fraction of a second. You can use specific ones to create atomic clocks for those that have interest.
No,